Hi folks, welcome to this video on a grab bag of a couple of different techniques in differentiation. So in this video we're going to look at differentiability again, which just means the places you can find slope, and we're also going to look at higher order derivatives. So in this very first one, does the algebra of differentiability. If you can't sub a number into f prime of x, then f of x is not differentiable at that point, typically. The algebra takes care of everything on non-piecewise functions. So if I were to think about this original function, which is x to the negative 1, its derivative is going to be negative 1, x to the negative 2, because power comes down front, power goes down by 1, or negative 1 over x squared. What number can I not sub into that derivative? Can't sub 0 for x. Okay. And what that means is that f of x is not differentiable at x equals 0. This technique doesn't tell us why it's not differentiable there. Maybe the graph would help you. You can see there's a discontinuity at x equals 0. Most importantly, the function doesn't exist there. It's outside the domain. We could do the same thing, though, for other ones. So if I wanted to find the derivative of this, it would be 2/3 x to the negative 1/3, or the derivative is 2 over 3 cube root of x. And again, can't sub 0 for x. It's not differentiable there. Again, it doesn't tell you why. If you were to look at the graph, the reason for that is that it has a sharp point there. It does exist, but the slope is not findable. But again, the algebra takes care of it for you. You can't put x into that 0 into that f prime function because it would cause division by 0. Okay, last one. We can differentiate here. We get 1/3 x to the negative 2/3. Or if you want to write that in radical form, it would be 1 over 3 cube root of x all squared. Now again, you can see you can't sub in 0 for x, so it's not differentiable at that point. If we wanted to look at the graph, we might understand why it's not differentiable at the point, namely that it goes vertical at x equals 0, and vertical doesn't have a number for slope. Slope is undefined. But just from the expression of f prime, we can tell that it's not differentiable at that point because you can't put in 0 into that derivative function. Higher order derivatives. This is going to shock you, but the derivative of the derivative is called a second derivative. So here are some common notations. You might see y double prime, or f double prime of x, or in Leibniz notation, you're likely to see this, d2y over dx2. And that will look weird because we'd expect the square to be in the same place on each of them. But there are good reasons for the units for leaving it the way it is. So if we find the first three derivatives on this one, y prime is going to be 2, 5x4 minus 4x3 plus 4 by 2x. Maybe you're feeling comfortable just doing these by showing less work at this point. Whenever you are, go for that. So that'll give me 10x to the 4 minus 4x cubed plus 8x minus 2. There we go. There's the first derivative. The second derivative just means doing the same thing again. So it'll become 10 times 4x cubed minus 4 times 3x squared plus 8 times 1, and the negative 2 will turn into a 0. So y double prime is 40x cubed minus 12x squared plus 8. Doing this again, we get y triple prime, where the third derivative is going to be 120x squared, because it's 40 times 3, minus 24x, because it's 2 times 12, and then plus 0. Okay, so we could keep going down. There are some practice questions around this on page 124. The last thing we're going to investigate in this video is differentiability on piecewise functions. So remember that differentiability really just means the ability to find slope. On piecewise functions, that means at those split points, we need to have them connect. We need to have them connect smoothly. And we need to have them connect non-vertically. So let's check out this function. If I'm drawing it, and I think it is worth drawing, it starts off as a line with a negative slope. And that is true right up until what I'll call its first split point, which is at -1. The corresponding y value, well, it just comes from putting in -1 into here, and I'll get 1. So that's where it stops being this diagonal line. I'm making it a filled-in dot because it includes that point. And after it's done being a line, well, then it takes up this parabolic definition. And so the question is, well, where does that start? If I put in -1 into this, I'll get 1. Okay, so there would be a hole here, but the hole's already filled. So it is connecting. Whether it's connecting smoothly or not, I don't really know. My graph is only so-so. And then the end of its parabolic definition is at 2. I put 2 into this function. That's 2, 4. That's going to be an open dot. 1. Here's 2, 4. And there we go. There's its parabolic section. And lastly, for this one, its split point, well, it takes up the definition of 4x minus 4 at 2. And if I put 2 into this, I'll get 8 minus 4, or 4. Oh, that's nice. That plugs this hole right here, this dot, and it goes on in a linear fashion forever and ever. So it is no longer a parabola, it's linear. So when I look at that, do they all connect? Yes, they connect at each of those handoff points, so I don't need to disqualify any of them at this point. If they had not connected, there'd be no point in investigating slope. Now what I'm going to do is I'm going to wonder what happens around x equals -1. What is the slope around it? Now, to the left and to the right of x equals -1. To the left, it's this line, this -x. So to the left, f of x has the definition of -x. Just to the right of x equals -1, it has its parabolic definition, or f of x is x squared. Now I'm going to think about the slopes. Okay, so the derivative of -x is -1. The derivative of x squared is 2x. And you might say, well, they're different, so that's no good. But we need to actually figure out what's happening, not just anywhere for slope, but exactly at -1. Now, this first one didn't have an x in it at all, so it's always just going to be a slope of -1. And this other one, if I put in -1, I'm going to get 2 times -1, or -2. What that means is that the slope from the left is -1, and the slope from the right of -1 is -2. They do not connect smoothly. So not same. Doesn't connect smoothly. It's not differentiable at x equals -1. There is a sharp point there. Our other point of interest is around the other pass-off point or split point, around x equals 2. And some people do this by showing the limits. I kind of like to just make this T-chart that says to the left and right. But it's up to you. You can make it more formal if you like. So to the left of x equals 2, we have the parabolic definition. F of x is that parabola. To the right, it's got its sort of final linear form, 4x minus 4. And what we're wondering is, if I put in 2 to the derivative, am I going to get the same slope on each of those? So f prime is going to be 2x here, and f prime is just going to be 4 in this other one. And then I'm going to sub in 2, which is the x value that we care about. And I'm going to find that at 2, from either definition, either that final linear one or the quadratic one, the slope's going to be 4. That means that this passes off nice and smoothly, and it looks that way on my graph. I did my best to do a half-decent graph. It turns from a parabola into a line very smoothly. Same slope, connects smoothly, therefore differentiable at x equals 2. This is pretty nitpicky stuff, but on a piecewise function, you might want that differentiability where they pass off. If you think about programming jumps in video games, like how different, like Mario jumps or somebody different, Celeste in the video game Celeste, they all have a slightly different arc to their jump. But when they have different definitions for parts of the jump, they need to pass off smoothly. Otherwise, the whole motion control feels very jagged. So that's one possible application of making sure that piecewise functions differentiate nicely at their split points. There's a practice sheet that you can do on this. I think it's in the video description. I hope this has been helpful. Good luck with the material, folks, and take care.